All right, next up is question 4. It says find a Cartesian equation for each curve described. Now, up above here for our reference are these key relationships that we've seen now a few times that relate polar coordinates r theta to Cartesian coordinates x, y. And so for part A, okay, we have the polar equation r is equal to 2. And given that r squared is equal to x squared plus y squared, I'm going to go ahead and start out by squaring both sides. So r squared is equal to 4, and then I'm going to go ahead and trade in r squared on the left side for x squared plus y squared, and that leads us to this Cartesian equation, x squared plus y squared is equal to 4, that describes the circle of radius 2 centered at the origin. Okay, now another way to think about this polar equation, r equals 2, is that it's describing the set of all points in the xy plane whose radial distance from the origin out to the point is 2 units. Okay, so this describes the set of all points on the circle of radius 2 centered at the origin. Okay, so this polar equation, r equals this constant 2, is quite a bit simpler than the Cartesian equation, x squared plus y squared is equal to 4. All right, now let's look at part B. Theta is equal to pi over 4. Now, given that tangent of theta is equal to y over x, I'm going to go ahead and take the tangent of both sides to start. So I get tan theta is equal to tan of pi over 4. As we just noted, tan theta on the left, that's y over x. Tan of pi over 4 on the right, that's 1. So we get the equation y over x is equal to 1. And then multiplying both sides of the equation by x, we get the Cartesian equation y is equal to x, and this describes the line through the origin with slope 1. All right, now this line forms the angle pi over 4 with the positive x-axis, and the set of all points in the first quadrant are the points where theta is pi over 4 and the radial distance r is greater than 0. And then if I take negative values of r, right, that's going to reflect these corresponding points in the first quadrant through the origin down here in the quadrant 3, and this gives me the set of all points where theta is pi over 4 and r is negative. Okay, so now we want to go ahead and generalize these two examples before we move on to part C. So first note that in the Cartesian, or what's also known as the rectangular coordinate system, setting x to various constants gives us a family of vertical lines, right? And setting y equal to various constants, that gives me a family of horizontal lines, right? And these blue vertical lines and these green horizontal lines partition the xy plane into a bunch of, well, rectangles, right? Hence the name rectangular coordinate system. Okay, now in the polar system, if I set x to a constant like I did in part A, right, that's going to describe the set of all points that are that constant distance away from the origin, right? So in other words, it's going to describe the circle centered at the origin, right? So if I let this constant vary, that's going to give me a family of concentric circles centered at the origin. Now if I set theta equal to a constant like I did in part B, okay, that's going to describe this line through the origin that forms that angle, that constant angle with the positive x-axis. So in part B, right, theta was pi over 4, and this corresponding line formed the angle of pi over 4 with the positive x-axis. Now if I let this constant vary, that's going to give me this family of lines through the origin. And these two families of curves now, the circles and the lines, they partition the xy plane, but you can see they don't partition the plane into rectangles. They partition the plane into these little windshield wiper looking, what are called polar wedges. Okay, so in the next section we're going to talk about finding areas of regions in polar coordinates, and so we're going to have to address how to go about doing that by filling the region out with these polar wedges. But in any event, let's go ahead now and press on to part C, and I need to first make a little bit of space. Alright, so for part C we're looking at the polar equation r times cosine theta is equal to 3. And looking up here and noting that x is equal to r cosine theta, we can then go ahead and just trade in r cosine theta on the left for x. And so we arrive at the rather simple Cartesian equation, x is equal to 3. Okay, so in this case, it's the Cartesian equation, which is the simpler one. And that's not really surprising given that this is just a vertical line. Now, a way I can interpret this polar equation, right, is that if I take any point on this vertical line, okay, well, the distance from the origin to this point, that's what we call r, and then this angle theta formed by the positive x-axis in this ray, okay, is right here. And looking at this right triangle in the figure, okay, the base of this right triangle, just using SOHCAHTOA, is r cosine theta. And you can see, right, that no matter what point you choose on this vertical line, r and theta can vary, but this base of the triangle, r cosine theta, will always come out to be 3. Okay, so this equation is just describing a vertical line. All right, now if we look at part D, very similar. We have r sine theta is equal to -2, and given that r sine theta is equal to y, right, get the Cartesian equation y is equal to -2, as you see right here. And so now, right, if I grab any point on this blue horizontal line, I can consider this right triangle and see if I slide this point around, the values of r and theta, they can vary, but what does not vary is the y coordinate of all of these points, which is just this height here you see in this right triangle. And so we're left with this condition that r sine theta, which is this height, always has to come out to be -2. Okay, cool. Moving on then to E, we have that r is equal to 3 over cosine theta plus 4 sine theta. Now, looking at these relationships, I like there to be an r cosine theta and an r sine theta, not just a cosine and a sine. Okay, so what I'm going to do to start out here, I'm going to multiply both sides of this equation by this denominator, because I note that since there's this r on the left here, okay, if I go ahead and distribute the r on the left side at this step, I get r cosine theta plus 4 r sine theta is equal to 3. And see, now I'm in good shape because r cosine theta is x, and then r sine theta is y, and so this leads us to the Cartesian equation x plus 4y is equal to 3. Now, this is a line in the xy plane, and so we can see here the Cartesian equation x plus 4y equals 3, quite a bit simpler than this corresponding polar equation. Okay, and then last up is F. We have r squared is equal to 2 cosine of 2 theta. Okay, now r squared, I know that's x squared plus y squared, so that's nice. On the right side, I have cosine of 2 theta. And see up here, I just have a cosine of theta and a sine of theta. So I'm going to go ahead and make use of a trig identity. I'm going to use the fact that cosine of 2 theta is cosine squared of theta minus sine squared of theta. So I'm going to replace cos 2 theta with this expression. And then, like I saw in part E, instead of just a cosine theta and a sine theta, I'd like there to be a r cosine theta and an r sine theta. And since the cosine and the sine are squared, I'm going to multiply both sides of this equation by r squared. Okay, now if I do that, I'll get an r to the 4th on the left side. And on the right, distributing that r squared, I get 2 times the quantity r squared cos squared theta minus r squared sine squared theta. And see, r squared cos squared, that's x squared. And r squared sine squared, that's y squared. On the left, r to the 4th, well, that's r squared squared. And as we noted now a few times, r squared is x squared plus y squared. So the left side is x squared plus y squared quantity squared. So we put all that together, and we wind up with the Cartesian equation x squared plus y squared quantity squared is equal to 2 times the quantity x squared minus y squared. All right, now this is a fairly complicated curve. This is this figure 8 curve known as a Lemnas Gate. Okay, you can see it here on Desmos there. And in this case, both the Cartesian and the polar equations are rather complicated. But I guess that's not entirely surprising given that the curve itself is rather complicated. All right, well, that's a good place to stop. I'll see you in the next video.